In this video, I want to take a look at what happens when you take the Laplace transform of a function times an exponential. Now, I start off here with the table of Laplace transforms that we've worked with so far. And it's quite possible that some of you noticed a pattern here. For instance, I see it mainly with these two down here, but it's true up above, that this is cosine bt, this is an exponential times cosine bt. And the difference in Laplace transform is just that it looks like the function has been shifted in the s direction, right? That this is e to the at, and you've got s minus a squared and s minus a. That is, all the s's here are replaced by s minus a's there. Likewise with the sine, right? That this is the Laplace transform of the sine of bt, and now we make the sine of bt times e to the at, take the Laplace transform, and what happens? The s over here gets replaced by an s minus a. It's just shifted in the s direction. Is that true up here as well? Because notice this one is the Laplace transform of t to the n, and now this is the exponential e to the at times t to the n. And what happens? It gets shifted. The s here gets replaced by an s minus a. It's just a shift in the s direction. And lastly, maybe the least obvious, but this is 1 and this is 1 times e to the at. And what happens? The 1 over s turns into a 1 over s minus a. The s is replaced by an s minus a. The graph gets shifted in the s direction by an amount of a. Okay. Is this a coincidence that this seems to happen every time? And the answer, of course, is no, it's not a coincidence. There's a theorem, and here's the theorem. It says if f is the Laplace transform, capital F of s is the Laplace transform of little f of t. If this exists for all s greater than some non-negative number a, and if c is a constant, then the Laplace transform of e to the ct times f of t is just the Laplace transform of f shifted in the s direction by c. It's f of s minus c. This happens anytime you can take the Laplace transform of f. If you multiply that by this exponential, then what you're doing is you're shifting the Laplace transform by c in the s direction. And conversely, if you know that the inverse, that should say inverse Laplace transform, yeah, that's better. If the inverse Laplace transform of capital F of s is little f of t, then the inverse Laplace transform of the shifted capital F of s. So f of s minus c is equal to e to the ct times f of t. Okay. To prove this, here's what I'm going to do. I'm going to prove the first part of it here, and I'll do an example of the second part. So to do the first part is just how do you do the Laplace transform of any function, right? You just multiply that function by e to the minus st and integrate it with respect to t from 0 to infinity. So the thing is, when you multiply by that exponential, then the two exponentials get together as e to this thing, negative st plus ct. You can factor out the negative t, leaving an s minus c on the inside there. And then this is just, I'm going to do it's not even a u substitution, because the integral here is with respect to t. I'm going to substitute capital S for s minus c. So just plugging that in there. I don't have to deal with it. I don't have to do a dt or whatever, because I'm not I'm not substituting for the integral, for the variable that's being integrated. I'm just substituting for some constants that are in there. So I'm going to call that s minus c, just capital S. But now this thing right here, this is what the definition would be for the Laplace transform of f, but with a capital S in there instead of a lowercase s. So this is f of s, but capital S is s minus c, and you've got the shifted transformation there. Okay, essentially multiplying by that exponential just changes the s into an s minus c. And so you have it shifted by c. This, I think, is remarkable because what we saw in the previous video was that if you shift your function, the Laplace transform gets multiplied by an exponential. This one is saying if you multiply your function by an exponential, the transform gets shifted. Kind of a duality there that's remarkable, which is why we remark on it. Let's do an example here. I want to take the inverse Laplace transform of this thing. Now, a couple things I noticed. Seeing the exponential on the transform side with the s's in there tells me that there must have been a step function involved, which then reminds me that, oh yeah, remember that the Laplace transform of u2 of t is just e to the negative 2s over s. So I've got the e to the negative 2s over, not quite s, but it's the shifted s. So this is like it's, just back up here, these are all s minus c's, and this is an s plus 2. So this is s minus negative 2, right? So there's apparently a shift of negative 2 here. But the s on the bottom is an s plus 2. The s on the top is not an s plus 2. Where the theorem says that this is f of s minus c. This is just the theorem from above. All of the s's have to replace by s minus c's. So when I look at this thing, I say the bottom s here is replaced by an s plus 2. I need the top s to look like it's been replaced by an s plus 2 as well. So what I'm going to do is I'm going to take that top s and just turn it into an s plus 2, which I can't do because that would change the function. But if I compensate to make it equal to what I had to begin with, then it's okay. So the thing is that s plus 2 is times negative 2, which means I've got an extra negative 4 in the exponent, so I can compensate by adding 4. Because if you multiply this all out, it just turns out to be the same as negative 2s. Right? But now I can change that numerator into this, because I can do e to this part times e to the 4. But then that e to the 4 is a constant, so it gets pulled out in front. And now I'm just looking at the inverse Laplace transform of this thing. And now this, slide down a little bit, this really does look like that with all of my s's replaced by s plus 2's, which means that the inverse Laplace transform is, yeah, u2 of t, but times e to the negative 2t. Because the shift here, remember, it was a c minus a, or an s minus c. So this is s minus negative 2, and so the c there is negative 2. So the e to the 4 was already out there, and now I've got this. This is essentially the end of this course. I have one more video to show you, just because we kind of end not quite making it to the punchline. That is, we don't actually solve any differential equations in section 6.3. In 6.4 we do. So in the next video I'm just going to show you one example of how these step functions can help us solve some real-world applications of, well, it'll be a spring problem.